Hi Wildcats, this is an overview of Unit 1 Focus Question 1 discussing periodic and simple harmonic motion. So on this slide you can see I have a bunch of pictures. These are all examples of either periodic or simple harmonic motion. So you might be able to see that they have some things in common. The most obvious, I think, is that all these objects are going back and forth, right? The kid on the slide or swing up here, the hand on the grandfather clock, all these things go around or go in some back and forth motion. And that, at the simplest of it, is really what periodic and simple harmonic motion are. So let's get into the specifics of them. So first, periodic motion. Periodic motion is just that. It is a motion that repeats itself over and over and over. So, right, the root word of periodic is period. So it has some specific like time of that cycle, and we'll get into that for a second, but it's a repeating pattern. Or it has a regular cycle where it has some position and then it ultimately gets back to that position. And there are tons of examples that we see every day, right? A clock. So the hour hand on a clock has one cycle. In order for this hour hand to come back to here, it's going to take 12 hours. So its cycle would be 12 hours. The minute hand takes 60 minutes to make one full cycle. The second hand takes 60 seconds. We see that in Earth, right? I mean, it takes one cycle of the Earth around the sun is 365 days approximately. The Earth revolves or rotates. It makes one full revolution every 24 hours on its axis. The moon rotates around the Earth about every 27 days. So these are all things that have a motion that repeats itself over and over and over again. All right, a student on a swing would be the same thing. They go back, forward, back. They ultimately are going to come back to this original position. So these are all examples of periodic motion because they have a regular cycle. So some vocabulary associated with that. First, period. I think I already started to define it. Period is the time it takes to complete a full cycle back and forth, to get back to its original position. So this is like a little pendulum here. So if it starts here, this object is going to then go from here to here. So that's half a cycle. And then it's going to turn around and come back, right? And so we could time that. We could get a stopwatch out and we could just ready, set, go, release it, time it for here and back. And then when it gets back here, we stop the timer. And whatever time that is, we would measure it in seconds. That is the period, the time it takes for one full cycle back from where it starts, away, and back to where it starts. So that would be period. Frequency is a little different, but yet related. So frequency is the number of full cycles back and forth in 1 second. So think about this. Frequency. The root word of frequency is frequent. Frequent means how often something happens, right? So how often something happens. So how many cycles happen in 1 second. So for frequency, we're always going to talk about how many cycles happen in 1 second. And the unit for this is the hertz. So it's abbreviated Hz, hertz, and so we would calculate this as 1 over the number of seconds, one cycle over the number of seconds, and that's how we would get hertz. So let's just make up some numbers here. Let's say I release this pendulum and I find that it takes, 2 seconds. It's a long time, but 2 seconds for it to go from here to there and back. Okay, so we would want to figure out in 1 second, how many cycles happen in 1 second? Well, you might be able to just get a general idea of this. If it takes 2 seconds to go from here to there, well then in 1 second, how many cycles are happening? Well, we can figure out that if it takes 2 to go all the way away and back, then halfway in 1 second, it's probably around here, so about 1/2. Well, we can math that too, right? One cycle happens in how many seconds? Well, we just said that one cycle happens in 2 seconds. So what is the frequency of this? The frequency is 1 over 2 seconds, or in other words, 0.5 hertz. So what does this 0.5 hertz tell us? It tells us that it makes half a cycle in 1 second. So the number of full cycles in 1 second, we get half a cycle in a second. Okay, so this is the difference. Period is the time for one full cycle. Frequency is how many cycles occur in 1 second. So for example, in this example, we get half a cycle in 1 second. Okay, so let's look at this in maybe in more practical application. If you've ever been to a carnival or an amusement park, they have these giant pirate ships that make you throw up, or spaceships or whatever, and you get on them, and all they do is they start here, and then they swing all the way forward, and then swing all the way back. And so they follow, that's periodic motion, right? Because it's following a repeating path, and it does so in some amount of time. So say I go to the amusement park, I get out my stopwatch and I time this, and I figure out that it takes 20 seconds to go from here all the way to the other side and then come back. So that's one cycle, or 20 seconds. So I just figured out I timed it. I timed its period. So its period is 20 seconds. So if I want to figure out what its frequency is, or how often something happens, I want to figure out how many cycles does the ship make in 1 second. Well, frequency is the one cycle over the period. So frequency is 1 over period. So I could just plug in my numbers here. Frequency is 1 cycle in 20 seconds. Would divide that out, and so I would get 0.05, 1 over seconds. And on the previous side, 1 over seconds is a hertz. So 1 over seconds, I could write 1 over seconds, but we would write hertz instead. So 0.05 is the answer I get when I take 1 divided by 20, and 1 over seconds is hertz. So this has a frequency of 0.05 hertz. Or in other words, in 1 second, it has gone 5/100ths of a cycle. Okay, so you might be able to see in this equation right here, frequency is equal to 1 over period. What that tells us, this is an inverse relationship. They are inversely related. Period and frequency are inversely related. What does that mean? It means as one goes up, the other goes down. So as period gets bigger, frequency gets smaller, which makes sense if you stop and think about it for a second. The longer it takes for an object to go through one full cycle, the less of a cycle you will have covered in 1 second, right? So if this went to 30, frequency would get smaller. And you can see I went the other way. Here's another example. Let's say the mechanism goes crazy. Now it's really going to make you vomit because it's going one full cycle in 5 seconds, much faster. So if we did that, we can see frequency is now it's still 1 over period, so one cycle is made in 5 seconds, so 0.2 over 1 second, or in other words, this ship now has a frequency of 0.2 hertz. So what does that mean? Because it's going through this full cycle in less time, I'm getting more of a cycle in 1 second, or it has a greater frequency. Okay, so that is periodic motion, a motion that repeats itself over and over. It has a regular cycle. We could time how long it takes for the student to go from here, or let's say from here. So we'll draw this out to go. This is their starting position. So how long does it take them to go from there, all the way back, all the way forward, and then back to here, right? That would be one full cycle because this is where they start. So we could time that. What is the time? That time would be our period, and we could figure out its frequency by taking 1 over the period. Okay, so that's periodic motion. So let's look at a special example of periodic motion, and that is called simple harmonic motion. Simple harmonic motion is still periodic motion, but it is the periodic motion that results when a restoring force is proportional to the displacement of equilibrium. All right, what does that mean? Well, first off, let's stop and talk about what restoring force is. Restoring force is any force that returns an object to equilibrium. So in this picture, I have a little different example, right? If I took like a ball and hung it from a spring and just let it sit there, it would settle out to some point. And that point is its equilibrium point. So this line represents its equilibrium point. And if I took this ball and I stretched out that spring by pulling on it and then let it go, what's going to happen? Well, the spring, the force, the spring will pull on it, and the spring will pull on it and pull it back up. Okay, so now it's going to go past its equilibrium point, and now the spring is all smushed up together, and so the spring is actually going to push on it, which will send it down further back to this position, which will then result in the spring pulling it back up and down and back and forth and back and forth. And what we get is this movement as a result of the restoring force around its equilibrium position. So back and forth, back and forth. That, simple terms, is simple harmonic motion. So just an aside here, what is a force? We haven't talked about these yet. And I think you all have an idea. A force is just a push or a pull. In physics, we use the symbol F for force, and the unit is a Newton, yes, after Sir Isaac Newton. So a Newton is a kilogram over meters per second squared. Again, more on that in a future unit, but this is what it means. So in this picture, we can see tons of forces, right? Like the student is pulling on the string is pulling on the block is pushing down on the ground, the student is pushing down on the ground. There are tons of forces, so pushes and pulls. Any push or a pull is a force, is the result of a force, and so we can just leave it at that. Okay, so now to look back at this restoring force, so we see the spring is pushing and pulling on this ball, and so therefore it is a force. Is it a restoring force? Well, does that force return the object to equilibrium? Yes, it does. Right. So in this picture, we can see it goes back and forth. So again, I stretch it out, which means now there is the force from the spring, which pulls it up. Then now it's up here. So we said the force from the spring would push it back down. And so again, you got to think about this as right? The spring is going to pull almost a little too hard. It's going to have momentum. It's going to shoot past its equilibrium point. So it's going to end up here, which means the spring is going to push it back down. But again, it's going to shoot past its equilibrium point. So now the spring is going to push it back up. The force from the spring is going to push it back up. So it'll go past it again and again and again and again and again and again and again. And what that results in is what we call an oscillation or a vibration. So if I graphed this position over time, of this, like its position here would be 0, here would be negative, positive, 0, negative, positive, on and on and on, I would get a graph that looks like this. Right? You've seen this before. It's a sine wave. And so this is going to link two waves in our next unit. But for right now, this is what we call an oscillation or a vibration. When an object goes back and forth around an equilibrium point, we say that it is vibrating or oscillating. Okay, so here's just another picture of that same system kind of in motion. Something we need to understand is that the restoring force is proportional to displacement. So displacement is just how far away it is, right? It's a little more than that, but for now we can leave it as it's just how far away. So what that means is restoring force is proportional to displacement. Proportional means when one gets bigger, so does the other. So as we increase the position of this, right? So as it gets farther and farther away from equilibrium, we can also see this restoring force arrow getting bigger and bigger and bigger. So as the object gets farther from equilibrium, the force also increases. So if we increase its position by 2 times, then the force will also increase by 2 times. And so the same thing, if we're increasing the force, then we know that its position has also increased. So this happens in simple harmonic motion because the farther we stretch this spring, the harder and harder it pulls, right? The more we compress this spring, the harder and harder it's pushing. So there's more force the farther it gets away from that. And that's a key characteristic of simple harmonic motion, is that the restoring force is proportional to displacement. As one gets bigger, or as displacement gets bigger, so does the force. Okay, one last term that we need to discuss here as we get through this is now we're talking about moving further away from our equilibrium position, and that is called amplitude. Okay, so amplitude is the maximum displacement from equilibrium. So how far away? Again, you see this sine wave. So how far away? So this is the amplitude. If we had a graph here and we could see the specific points, we could say that this right here is its maximum amplitude. Let's say we measured this and it was amplitude is equal to 0.25 meters. Okay, so that's amplitude. And so in an oscillation, we see this repeating pattern of amplitude where it goes from zero, right, zero amplitude because it's at equilibrium, to some positive amplitude, then it goes back to zero amplitude, then it comes down here to negative amplitude, which will be the same 0.25 meters. But negative, right, because now it's below my equilibrium position, and then it's going to come back to equilibrium. So this right here is one full cycle. And if we had a timer out, we could time that and we could figure out what is its period. So that tells us there's a relationship between amplitude and period. One period occurs when an object has gone through 4 amplitudes. So here's one amplitude from here. I'll do it in a different color. From here to here is one amplitude, so that's A. From here to here is 2 amplitudes, so there's an A. So here's A. Get this pen to work right. I apparently cannot. There we go. Okay, so here's another A. From here to here is another amplitude, and then from here to here is another amplitude. So that's 1, 2, 3, 4 amplitudes in one period. So there's a relationship there. Okay, so hopefully that helps in terms of understanding not only the difference between periodic and simple harmonic motion, but also terms associated with them that we use to describe them, such as period, frequency, and amplitude.